Here's the Zoom meeting for Physics 232C, March 4th, the first day after spring break. Well, for the next few days, we'll be studying Chapter 20, Part 1 on electromagnetic waves. So you should read the first half of Chapter 20 and take notes. You should recognize these equations. They should be in your notes. First of all, what is an electromagnetic wave? It's a wave. The electric field points in one direction. The magnetic field points in a perpendicular direction. And the wave travels in the third dimension. So you should be able to draw a picture of an electromagnetic wave. These are the equations. We'll see an example of that in a minute. A plane wave, the simplest kind of wave, depends on various parameters. For example, the electric field oscillates between a maximum value E0 and a minimum value negative E0. It changes sinusoidally in position and also sinusoidally in time. So it oscillates in both position and time. The magnetic field also oscillates in position and time in exactly the same way. So the magnetic field follows perfectly the electric field, except the field vectors are perpendicular. Now, there are many parameters that describe waves. You'll think back to Physics 231. There's the wavelength. That's related to this parameter k. Lambda is 2 pi over k. That's wavelength. Period of oscillation is 2 pi over omega. The wavelength times the frequency, that is to say, the wavelength divided by the period, is the speed of the wave. And for electromagnetic waves, we all in empty space, we always denote that by c, lowercase c, which is the speed of light or the speed of other kinds of electromagnetic waves. And what Maxwell proved is that these fields propagating as waves have a speed which is universal. In terms of the parameters we've used earlier in this semester, mu naught and epsilon naught, c is 1 over the square root of mu naught epsilon naught. There's also a relation between the amplitude of the electric field oscillations and the amplitude of the magnetic field oscillations. It can't be equal because they have different units, but they're proportional, and the constant of proportionality is a universal constant. It's just the speed of the wave. So those are the properties of electromagnetic waves. We also need to understand the energy in electromagnetic waves. You remember from earlier in the semester, electric fields have energy, magnetic fields have energy. The energy density, so U is not the energy, it's the energy density. It's 1/2 epsilon naught E squared plus 1/2 1 over 2 mu 0 B squared. Now, it turns out, as Maxwell discovered, the electric energy and the magnetic energy are equal. So E0 is B0 times C, and C is 1 over the square root of mu epsilon. So in fact, the electric field energy is exactly the same as the magnetic field energy. Now, we usually express this in terms of the average energy. Remember, E and B are both oscillating in time. So E will oscillate between 0 and some maximum value squared. B similarly. So we usually express the average in time of the energy density. E squared oscillates between 0 and E naught squared. So the average is 1/2 E naught squared. And B squared oscillates between 0 and B naught squared. So the average is 1/2 B naught squared. So the average energy could be written either this way: 1/4 epsilon naught E naught squared plus 1/4 mu 0 B naught squared. Or you could recognize that these two are equal, and you could write it as 1/2 epsilon naught E naught squared. Or you could write it as 1/2 mu 0 B naught squared. That's the energy density at a particular point in space. Now, of course, the wave is propagating in space in some direction. For this formula, it's moving in the z direction. So the wave moves in the z direction. The electric field oscillates in the x direction. The magnetic field oscillates in the y direction. What's the energy transport? We call that energy flux. We use the symbol S for energy flux. These are some ways to write the energy flux, but those aren't really the best ways to write energy flux. This is true, but it's not really the best way to write it. This is true. That's for the time-dependent energy. This is for the time average energy. But these aren't really the best way to remember these quantities. The best way to remember this is that the average energy flux, that's called the intensity of the wave, or the brightness. Intensity is energy flux, averaged over time. It's the energy density, which we can write in various ways, times the speed of the wave. So energy density has units of energy divided by volume, joules divided by meters cubed. Energy flux has the unit of energy density, that's joules per cubic meter, times speed, that's meters per second. So that's joules per square meter per second, or joules per second is watts, so that's watts per square meter. One property of electromagnetic waves is called polarization. In what direction is the electric field oscillating? Well, if I write it here, as I've written it here, it's in the x direction, but it could just as well be in the y direction or in the z direction. It just have to be perpendicular to the direction of motion. It could just as well be at a 45-degree angle to the x direction. Anyway, the direction of the electric field oscillations is called the polarization. And there's a relation between intensity and polarization called Malice's law, which describes how polarizers reduce the intensity of light. Now, the speed of light c is a universal constant. Maxwell, taking his field theory, discovered that c is just a constant. It's 1/square root of mu epsilon. And when he plugged in the values of mu, that's the magnetic force constant, and epsilon 0, That's the electric force constant. And then he took 1 over the square root of that. He found the value of C is 2.998 times 10 to the 8 meters per second. Now that was already known in Maxwell's time to be the speed of light. And so Maxwell said, since in my theory of fields, the electromagnetic waves travel at the speed of light, I conclude that light is an electromagnetic wave. And that's how people discovered light is electromagnetic, an electromagnetic phenomenon. This will be very important in part 2 of chapter 20. All right, so let's take a look at some problems. Here's one of the problems from the homework assignment. The homework assignment is due Wednesday. Suppose you have an electric field where Ex is 0, Ey is 0, Ez is A sine kx minus omega t. This is a wave polarized in the z direction. So the electric field is oscillating in the z direction and traveling in the x direction. So the magnetic field will be perpendicular to both of those directions. It'll be in the y direction. And in this problem, you're supposed to calculate from this information the frequency, the wavelength, the amplitude of magnetic field oscillations, and the intensity. Not really called time averaged intensity, it's really just called it's really just called intensity. Now, what's given in the problem? Well, the value of A is given. That's an electric field strength, so it has to have units of the electric field. Let's say it's 6 volts per meter. And omega is 2.8 times 10 to the 8th. What are the units of that? Well, I take the sine of omega t. So omega t has to be sort of an angle. We can just say the unit of omega t is radians. And so t is in seconds. So omega has to be radians per second. And it says here 2.8 times 10 to the 8 radians per second. So in all problems, we start by drawing a picture. So here's a picture. The electric field, well, I don't have this picture right. The electric field is traveling in the x direction. So that's the x-axis. The electric field is oscillating in the z direction. The magnetic field is in the direction perpendicular to x and z, so it's in the y direction. So here's the electric field oscillating in the z direction. That's Ez. Here's the magnetic field oscillating in the y direction. And here's the x direction. That's the direction of propagation. So that's the picture. Now what are we supposed to calculate? Frequency, wavelength, amplitude of the magnetic field. We already know the amplitude of the electric field. It's 6 volts per meter. Well, what's the amplitude of the magnetic field? And the intensity. That's what we call S average. It's the average of the energy flux, the energy flow. So we start by drawing a picture, then we write down the equations. So here are some of the equations we're going to need. Frequency is omega over 2 pi. That's angular frequency divided by 2 pi radians. Wavelength is the speed over the frequency. The speed of the wave is one wavelength divided by one period. You know, in the time that the wave undergoes one period of oscillation, it travels by a distance of one wavelength. So it's one cycle in space and it's one cycle in time. So the speed is, so the wavelength is the speed divided by the, divided by the frequency. So in other words, the wavelength, to understand that equation, the wavelength is the speed, that's c, times the period of oscillation. That's t. We call that period. And now frequency is 1 over the period, 1 cycle per second. B naught is E naught over C. The intensity is the average energy density times the speed of the wave, that's C. So we can, from these equations, given E naught, remember E naught is A, that's given, and given omega, so omega is also given. Well, from here we can calculate F. Once we know F, we can calculate lambda because C is 3 times 10 to the 8 meters per second, 2.998 times 10 to the 8 meters per second. So we can calculate lambda. From this, we can calculate B0. And now what about the intensity? Well, it's the energy density times C. So we could express the energy density as 1/2. Let's see, I'm not doing too well with making these. See if I can do it this way. That's not what I want. This is what I want. One half epsilon 0 E 0 squared. Now that would be the average intensity, the average energy density, both electric and magnetic, and now multiplied by C. Epsilon 0 is a universal constant. E0, we have it here. E0 is this A. Okay. Okay, find the wavelength range for AM radio. That has frequencies from 540 kilohertz to 1,600 kilohertz. And FM radio. That has frequencies from 88 megahertz to 108 megahertz. So we always start by drawing a picture. Well, here's a picture of an electromagnetic wave. This could either be the electric field oscillation, or it could be the magnetic field oscillation. It would just have to be in some direction perpendicular to the direction of motion. And one wavelength can be defined in various ways. One way is to say it's from the crest to the next crest. The crest of the wave, the maximum amplitude, to the next crest, the next maximum amplitude. That could be one way to define the wavelength. Or you could say it's from one node to the next node. Well, two nodes. It's from one node where the intensity is increasing to the next node where the intensity is increasing. That's the same as the distance between two crests, two maxima. And the wavelength over the period is the speed of the wave. Because if this wave moved by one wavelength, so if it moved from here to here, that is, it moved a distance lambda, it would undergo one complete oscillation in time, from maximum to minimum back to maximum. That's one complete oscillation. So in the case of AM radio, well, the minimum frequency is given as 540 kilohertz, 5.4 times 10 to the 5 inverse seconds. The wavelength is then the speed, let's say approximately 3 times 10 to the 8 meters per second, divided by the period, 5.4 times 10 to the 5th inverse seconds. So the 1 over seconds in the numerator cancels the 1 over seconds in the denominator. This is roughly 30 divided by 5 would be 6 times 10 to the 7 minus 5 would be 10 squared. So it's about 600 meters. So that's AM radio. It ranges from the longest wavelength of about 600 meters. To calculate the shortest wavelength, we would take the maximum frequency. Wavelength and frequency are inverses. So the maximum frequency gives us the smallest wavelength, would be about 200 meters. And there's also part B, the case of FM radio. Here's another problem from the assignment, which is due Wednesday. A point-like source of electromagnetic waves radiates power in all directions at a single frequency. So at a distance r, let's identify this parameter r, that's the distance from the source. A detector will measure intensity. Remember, that's the average energy flux to be S average. So there are two quantities given, R and S. This really should be S average. So I have those two parameters specified. And now the question is, what's the amplitude of the magnetic field oscillations? So that would be B0. The magnetic field oscillates between a maximum value B0 and a minimum value negative B0. So that's the first question. The first question is, what's B0? And then the second question is, what's the total power? So let's call that total power P. So we always draw a picture. Here are the wave fronts. Here's some kind of something emitting light could be a flame. Well, these are actually going to be more like, well, I don't know whether these are light waves or radio waves or even X-rays. Just here's some source of a kind of electromagnetic waves. Maybe it's microwave. So this is a microwave tube. And away from the source, there are spherical waves propagating away at the speed c. In all directions. So here they're moving at the speed c. Down here, they're moving at the speed c. So at any particular time, there's a radius, c times that time, where the wave fronts, let's say the crests of the waves would be at that radius. Now the questions concern energy, like power. So let's think about, well, this is all wrong, actually. That part is wrong. So what we want are formulas let's see. We want a formula for S. Because I have S as a given quantity. Well, if I write it in terms of the magnetic field, S is, let's see if I can do this. S is 1 divided by 2 mu 0 B 0 squared, that's the energy density, multiplied by C, that's the speed. So you see, I can write an expression for B0 in terms of S. And that's what I would put here. S is equal to, sorry, B0 is equal to square root. Let's see, I have to multiply both sides of the equation by 2 mu 0. So here would be 2 mu S, 2 mu 0 S in vacuum, divided by C. Now, in this problem, you're supposed to give the answer in the form of formulas. So what would go in this box here is the square root of 2 mu 0 S divided by C. And then for part B, it's the total power. Now, S is power divided by area. S is energy flux. So it's energy per unit time. Energy per unit time is power. Energy per unit time is joules divided by seconds. So that's watts. So that's P. And what's the area? Well, all of the energy goes out through a sphere, any sphere of radius r. So let's take this distance to be r. Any sphere of radius r, all of the energy goes through that sphere because the waves propagate out in spheres. And so what I need here is the area of a sphere. Well, the area of a sphere is 4 pi times the radius squared. So what I want to calculate here is the power So the power would be 4 pi r squared s. All right, so there are some examples of what's in this chapter 20. It's the first 3 sections of chapter 20. You have to know the meaning of electric and magnetic fields in an electromagnetic wave, the various parameters, wavelength, period, frequency, speed, amplitudes. You need to know about the energy in electromagnetic waves. These equations, let's see. These equations are not in the book. So ignore those equations. But these equations for electric field are in the book. In fact, we've seen these equations in previous sections, previous chapters. And intensity is average energy flux. And we've seen a couple of examples of these in these problems. Now, this is Monday, the 4th. That's chapter 20, part 1. Next week, or after Wednesday, is section 20, part 2. And then will be the second hour exam, the second midterm exam. So let's see. The midterm exam, this assignment is due the 6th. The next assignment is due the 13th. And the exam is March 14th. So we're spending 2 weeks on this chapter 20 because it's quite important. Now let's see, are there any questions? Let me look on the chat board. Somebody left a question on the chat board. All waves here should always be the speed of c. Yes, all electromagnetic waves, light waves, radio waves, X-rays, microwaves, they all have the same speed, c. Now that's the speed of the wave in empty space. The speed is affected if the wave goes through some kind of transparent material. So for example, the speed of light in glass is a little bit smaller than the speed of light in empty space. But anyway, that comes to a later chapter on optics. Meaning that anything we calculate a result with speed c is an electromagnetic wave. Yes, electromagnetic waves are the only thing in the universe that travel at that very high speed. No particle can travel faster than the speed of light. That'll be part of chapter 20, part 2, relativity.